Okay, well, let us talk about around 1938. So a lot has happened by this time in our historical survey. Hitler became Chancellor of Germany in 1932 or 3, one of those. Yeah. He then started passing laws against the Jews. 400 academic Jewish Germans lost their job immediately when he passed his first law, I think in April 33. And the emigration began of eminent Jewish scientists. Oh, look at your shirt. I love that shirt. Here, come up here, Kayla. I want everybody to see the shirt. Whoa, look at this shirt. Everybody know what this shirt is.
Nothing too fancy and down Market Square.
Oh, beautiful shirt. You know what this is?
Yeah.
That's Tennessee. That's all at 117. So I've been telling you about, well, see right there, 109 is named after Lisa Meitner. And 117 is named after the state of Tennessee because Oak Ridge National Lab, Vanderbilt University, UT recently involved in these experiments. So we're trying to do that in Russia, resulting in the discovery of 117 and 118. Now it's about 2 years ago. So congratulations, I love your shirt.
What was the name of the store again?
Right. Gee, that's extra points.
Yeah, there you go.
So then, you know, of course, Fermi, Enrico Fermi, the great Italian physicist working in Rome, did the crucial measurements, did a series of measurements after the neutron was discovered in 1932, that he could induce artificial radioactivity in atoms, in nuclei, by projecting a weak flux of neutrons onto different targets or different elements. And he then, when it got to uranium, and hit uranium, the heaviest element in nature, element 92, with neutrons, he found new radioactivities. Did some rudimentary chemistry and had the conclusion that element 93 and or 94 had the chemistry of lanthanum, which made no sense. This started the world thinking. Marie Curie's daughter, Irene Julia Curie, led experiments at the Radium Institute in Paris. And in Berlin, Lisa Meitner was the head of the physics department in Berlin. She was Austrian. So even though Hitler started driving the Jews out of Germany, she was safe because she was not German, she was an Austrian Jew. And so she continued in her work at the Kaiser Wilhelm Institute, working on this conundrum of what do you get when you hit uranium with neutrons? What are you making? How could element 93 or 94 have the chemistry of lanthanum or barium? So, but then on March 12, 1938, Hitler annexed, absorbed, took Austria. So then Lisa Meitner became a German Jew, and she knew she was in trouble. It was even worse by now. By now, there had been such a flux out of Germany of very good Jewish scientists that Himmler, especially, the SS, was starting to change the rule that if you were Jewish, you could no longer leave Germany, which was the Italian policy by this time under Mussolini. So Dutch friends, Dutch colleagues, Dutch physicists came to Berlin to convince Lisa Meitner it was time to go. She had to go quickly. They helped her pack her bags. They got on a train, took her to Holland. They were very nervous when German authorities mounted the train at the border to the Netherlands. And she was afraid that she might get taken. Then, since her passport was stamped Jewish, somehow this was a new rule of not allowing any more academics, Jewish academics to leave Germany. She got through, she got to Holland, they took her to Copenhagen. Niels Bohr, the Nobel laureate in Copenhagen in Denmark, welcomed her, got her arrest, and found her position in Stockholm. And Sigmund was the great Swedish physicist who won the Nobel Prize in 1932 for X-ray spectrometry of elements. Took her in. It was not too happy about it, didn't give her any money, but gave her a place to hang her hat, so to speak. And so she set up shop in Stockholm while her group continued experiments. You know, at the same time, a lot was going on in the world. I mentioned this a little bit last time. Hitler wanted to unite all of the German, predominantly German-speaking parts of Europe. And after World War I, parts of Czechoslovakia, this is a map of Czechoslovakia as it was before World War II. And after World War I, Czechoslovakia was formed, this new country. Different things were packaged differently than before World War I. And these then colored indicates how much German-speaking people are there, what percentage. And so you see Germany's up here. So this borders with Germany were heavily German-speaking parts of Czechoslovakia, and also other borders here of Czechoslovakia, heavily German-speaking. Well, Hitler wanted that for his own, and that was called, at that time, the Sudetenland. That those were primarily German-speaking parts of Czechoslovakia, and after he took Austria, that was next on his list to reunite, which was once part of the German Empire. So he then started a series of meetings. He tried to bully the Czechoslovakian government to initially, and of course, the French and British governments were involved because they had treaties with Czechoslovakia, especially France. France and Britain argued that there should be self-determination. Those primarily German-speaking parts of Czechoslovakia. Let them decide if they wanted to join the Third Reich, whether they wanted to stay part of Czechoslovakia. The famous Neville Chamberlain met with Hitler several times, felt he had a promise from Hitler that Hitler would respect self-determination in those parts of Czechoslovakia. Of course, Hitler did not. There were several meetings. Hitler moved in and took those parts of Czechoslovakia. And there, in spite of his promises, there was a final meeting between Chamberlain and Mussolini and the head of France. And once again, Hitler promised that there would be no war, that this was all he wanted, was just these German-speaking parts of Czechoslovakia, that he'd be a good boy, wouldn't go any further. Of course, that was all a mirage. After that meeting that day, in September of 1938, he and Mussolini met that evening to discuss how they would together invade Britain. So Hitler was not going to be satisfied with just the what was called the Sudetenland. He wanted all of Czechoslovakia. In part, he wanted Czechoslovakia because that would be a buffer to Russia. He knew that invading Russia was next on his list also, going east, not just west. And he needed Czechoslovakia to be a buffer to help him protect against the Russians after he invaded them. And so the German-speaking peoples of this part of Czechoslovakia, his son welcomed him. He rolled into one of the cities up near Eger in October of 1938. So that was part of his plan to expand east in addition to west. Experiments continued in Berlin. Lisa Minor had to leave. She was in Stockholm now, so she was no longer part of this. Otto Hahn was the head of the institute. He reported to her. He was one of the world's best radiochemists, nuclear chemists, and also involved were the Curie team. Marie Curie and her husband, Pierre Joliot, were doing experiments in Paris. They were scattering neutrons off of uranium. They found a 3.5-hour radioactivity that had not been seen before. Something when you hit uranium with neutrons. What was it? What element was it? Of course, they did chemistry in Paris. They found that it precipitated out whatever they made. You radiate and you took the sample out with this 3.5-hour radioactivity, and you did chemistry on it. They found that it precipitated out with a lanthanum carrier. Well, that was strange. See, lanthanum is part of the lanthanides. All these have similar chemical properties. And let's see, did I have this in? Well, the fact that it would have the chemistry of lanthanum did not make sense. You see, if you were making element 93 or 94, it should have a chemistry over one of these, manganese or whatever. It's not known about the chemical properties of the actinides. So this is a newer periodic table. The fact that it had a lanthanum like chemistry did not make sense. And of course, you couldn't. There's no way you could hit this big uranium nucleus with 92 protons with a neutron and somehow make lanthanum, which is element 57. How would you eject all of those protons and neutrons just by hitting uranium with a slow neutron? Made no sense. They published their paper in 1938 in September. Hahn and Strassman, Meitner was now in Stockholm, so they started new experiments in Berlin to try to address this conundrum. They bombarded uranium with neutrons. They found 16 new radioactive species. They used various tracers. Tracers when you add barium, for example, to whatever you're trying to understand, and then you see new chemical separations. If the mystery thing you made is barium, it would precipitate out with barium or with lanthanum. So you use various precipitators to try to see where does the radioactivity go as you mix in different trace elements. And as they did those experiments, they found that 3 of them precipitated out with barium. And so they thought, well, it can't be barium. It can't be barium, for goodness sakes. That's only 56. How do you get rid of 36 protons plus neutrons? So it's got to be radium. Radium and barium would have the same chemistry, the first order. That's what they published. And so they said, the way you get radium by hitting neutrons on element 92 is by evaporating 2 alpha particles. Alpha particle is helium. That's 2 protons, 92 protons in uranium minus 4 protons makes radium. Voila. But that didn't make sense. Meitner read that paper. Niels Bohr read that paper and said, there's no way, physics-wise, that you would have enough energy to evaporate 2 alpha particles. Physically impossible. Meitner was in Stockholm. Hahn wrote to her saying, don't know how you do this. And they described some of their experiments. Could it be barium? Or could it have the chemistry of barium? Well, they started, therefore, a new series of experiments in December of 1938. Middle of December, they focused on a certain activity, 81-minute radioactivity that you make when you hit uranium neutrons. Supposing activity of radium. chemistry of barium, so it can't no way it can be barium. It has to be radium, even though Niels Bohr said it's impossible. So they then performed various experiments on December 17th. They did an experiment not just on the primary radioactivity produced, but then on the decay of that. You see, if the activity is radium, that's element 88. And then we go by beta decay with that activity, with that 86-minute half-life, would decay to actinium, so 89. Well, that has a different chemistry. Actinium is up here, down here. This element here. So the mother and the daughter would have different chemical activities, different chemical fingerprints. But for really barium, they would decay to lanthanum. Element 56, decay to 57. And so that's what they focus on, not only doing the chemistry looking for the mother activity, but also of the daughter activity after beta decay. And they were amazed that they could separate lanthanum from actinium. Sorry for this. Let's go to the previous one. You could separate this from lanthanum by chemical fractionation. There is a process to separate this element, even though they're the same family, same class of elements. You could separate this from this. And that's what they focused on. Otto Hahn and his hotshot chemistry sidekick, Fritz Strassmann. And to their shock, they found that the decay product, after they did that separation, was not actinium, it was lanthanum, which meant that the primary activity had to be not radium, but barium. How on earth could you make barium element 56 by hitting uranium with one little slow neutron? Made no sense. Hahn wrote immediately to Lisa Meitner in Stockholm, asking for advice. Meitner was the physicist. Hahn was the chemist. He deferred to her. Don't chemists generally do that? Of course. Mark is a chemist by training. He wrote to Lisa Meitner for advice on what's the physics of this? How is this possible? If this is what the experiments indicate.
Chemists become chemists because they're not good enough to do the math. Physicists.
So that's why he wrote to Meitner. Right. Well, this was December 17th. Hahn knew he had a very important experimental result. He knew well the editor of the physics journal in Europe. They published this. He got him to agree that on December 23rd, Hahn had to submit his paper for publication. You got to publish this quickly. He knew that the French were working on this. Other labs were working on this. This was shocking, this result. He wrote to Meitner, before I write our paper, explain this to me. What's the physics of this? Well, the Christmas holiday was coming up. He wrote to Meitner right away on December 17th, of course, before email and such like that. And he waited for her to reply with a physics explanation so that he could put her name on the paper. She got the result. She got the rudimentary first draft of the paper. But then she was due to leave. You know, she was living in Stockholm without family, without friends, really. Her nephew, Oliver Frisch, was in Copenhagen by this time. He was also Austrian, Jewish. He left Germany earlier to go to Copenhagen to work with Niels Bohr. They decided they would meet, aunt and nephew, in Western Sweden over the Christmas holidays. They met at a hotel just to stay for a week over Christmas near Göteborg, not far across the Øresund from Copenhagen, a little bit north of it. And they stayed in a hotel, and they were worn out the first night. Then the next day they met for breakfast, and Lisa Meitner showed her nephew, Otto Frisch, this letter from Han saying, my goodness, it's barium that they're making. And neither understood it, so they went out for a walk. Lisa Meitner, was a big time hiker and walker, went out for a walk in snow-covered area around Göteborg in Sweden. And they, how could, there's not enough energy with this little neutron to knock out 100 particles, 38 neutrons, 36 neutrons, protons plus neutrons. You have to evaporate 90 or 100 particles to get down to barium from uranium. So they went out for a walk. Otto Frisch and his aunt, Lisa Meitner. And, Otto Frisch had just heard a seminar from Niels Bohr the previous week in Copenhagen saying that nuclei could be viewed as a liquid drop. And that was a new concept, that sure, you've got neutrons and protons moving around inside the nucleus, but at the macroscopic level, you might be able to view nucleus as a liquid drop. And the liquid drop would be, especially for something big like uranium, would be a rather big and flabby nucleus. Because you've got the nuclear force inside between neutrons and protons. That is attractive. So that's what's holding the nucleus together. However, you also have the electrical force between protons because they have a charge. They have a positive electrical charge. Like charges repel, so you've got the electrical force pushing the protons apart. The neutrons are like nuclear glue. But the point is that this force, let's say, is short range. It's a strong force, but it acts only over very small distances. The electrical force, however, long range. The force decreases as 1 over the distance squared. So the force does get weaker as you separate the two protons, but it never goes to zero. And it's therefore long range. So for a big nucleus like uranium, it's a tenuous nucleus that's barely held together. Electrical force trying to push it apart, the nuclear force trying to hold it together. Therefore, you took and this is what they calculated, that if it were a liquid drop, more or less, you have a deformed uranium nucleus, football shape more or less. You hit it with a neutron, and a little bit of energy doesn't break it apart, doesn't split it, but it starts this liquid drop oscillating. It's like a dumbbell. Goes out and forms a dumbbell shape, and then it goes back together. It goes somewhat unstable. And if that neutron has just enough energy, it might then cause these two parts to separate, because now they're further apart than here. That long-range Coulomb force, electrical force, pushes the pieces apart, overcoming the attraction of the nuclear force. And then they could split into two. Well, Frisch had just heard this lecture, sat down literally on a tree stump in a snow-covered forest, took out a piece of paper and a pencil, and calculated that, gee whiz, if that were to happen, the amount of energy released by that split, by that breakup, would be huge, be on the order of 200 MeV. You don't understand that unit necessarily, but the point is that atomic processes, chemical transitions, emission of light, electrons in an atom give off energy 1,000,000 times smaller, maybe 5 electron volts. Now, Frisch calculated that if you split this apart like that, you could have the release of energy that would be about 40 million times larger. With a stunning thought, that is. And so that might be then how you get barium. Because you split the uranium nucleus in two. Barium is roughly half the size of uranium. That's how you would get barium. And you would get a lot of energy given off in that split. Well, that was a stunning original thought.
So is
Yeah,
that
Bill.
energy coming from the mass?
Yes. Bill's right. The energy comes from V equals mc squared. They knew that after 1905. So that's the 200 MeV given off. It comes from the fact that the mass, I'll explain this more later. But the mass of two fission products, we call it now, two pieces, is greater than, no, is less than the mass of uranium. So in that split, these two pieces weigh less than this, because these are more tightly bound. It's binding energy per nucleus. And when this then splits into two, you got to get rid of mass. And you got to get rid of it by E equals mc squared, by emission of energy. And that's the energy that drives nuclear power, nuclear bombs, and so on. And no one understood that, thought of that, until Frisch and Meitner sat down on a tree stump around Christmas of 1938. A lot started happening very quickly then. Meitner went back to Stockholm. Frisch rushed back to Copenhagen. He went immediately to see Niels Bohr to explain that. I mean, the world knew, the rumors were circulating about, well, Frisch showed Bohr the letter from Otto Hahn that, geez, it is barium that you make when you get uranium neutrons. But of course, that was a conundrum that was done in the world. People were trying to understand Fermi's experiment from 1935. They indicated that maybe something you made by neutrons on uranium had the chemistry of lanthanum or barium. And people have been, physicists, been trying to understand that. Frisch showed Bohr the letter from Hahn to Meitner, explained to him, to Bohr, this idea of a liquid drop splitting in two, and Bohr said, oh my God, why didn't I think of that? To explain the conundrum that Fermi first pointed out in 1935. So finally, Bohr, the great Bohr, started to understand what was really happening when you hit neutrons with uranium. It splits into two. Really unexpected. Frisch and Meitner prepared a short paper by telephone to describe their explanation. Hahn and Strassman's paper was published on January the 6th, 1939. That was very quick. Things all happen that quick. Right? Bohr, it's a good thing that Frisch got to Bohr because he was due to get on the ship in on January 8th to go to New York. This is before World War II had really expanded a great deal. Hitler was taking Czechoslovakia, Austria, but you know, the Brits, Chamberlain thought that, well, he'll be satisfied. There will not be a big war. We'll placate him. He's a good guy, actually. So Bohr had planned, was going to work at Princeton, which is where Einstein was. He was due to leave on a ship on January the 8th, and Frisch luckily got to see Bohr the day before to give him this news before he realized he'd been dumb and missing an explanation of this conundrum. Frisch came back to Copenhagen. He did a confirming experiment using an ionization chamber to actually detect the fission fragments, the two pieces that uranium split into. So there were two things given off, two nuclei smaller than uranium. He confirmed that. By the way, William Arnold was an American biologist who was visiting Bohr's Institute that December and January, and Frisch excitedly told William Arnold, a biologist, what was happening. Uranium was dividing, splitting into two. What do you call that in biology? Cells do that in biology. And Arnold described, well, we call that cell fission. And therefore, Frisch in this paper with Meitner said, okay, we'll call this uranium fission. And that's where the term came from. I did not know that. Is that right? Is that the same Arnold?
He did, in fact, I've written an article about Bill Arnold.
Okay, he was in the National Academy of Sciences.
Yeah, I think so.
Oh,
He,
well, I learned something new.
he was,
Don't take this off.
Is that right, Ray?
had at least two claims to scientific fame, according to the article here. Carolyn
Come up
Krauss.
here so Tamara can see.
Yeah, let's get this. Carolyn Krauss wrote this for Historically Speaking. And I'll read just a little of it. William Arnold, a plant physiologist, physicist, and biologist, employed in Oak Ridge National Laboratory's Biology Division from 1946 until 1970, had at least two claims to scientific fame. One claim was his set of scientific discoveries on the effects of light on the vital process that makes green plants grow. You grow in Oak Ridge. That's my slip of the tongue. Makes green plants grow. The other was his contribution to the term fission, used to describe the process that makes nuclear power plants work, what we just talked about. Some Oak Ridgers remember that the pipe-smoking Bill Arnold kept a blackboard in his living room. Leanne Russell, former section head at the ORNL Biology Division, recalled that he built a fallout shelter under his Semesto house. One of Arnold's two daughters, Helen Perrin of Indianapolis, supplied some photos, wrote in a journal dedicated to her father that he considered himself lucky to have been able to make a living doing what he would cheerfully have done for free. She noted her father's sense of humor and easy way with people reflected his self-confidence and his enjoyment in life, friends, and science. He was a Wyoming native. He died in 2001, and he contributed greatly to the understanding of photosynthesis. And when he came to Oak Ridge, he'd already made a name for himself through his research in 1932 with Robert Emerson. That's where the two of them discovered photosynthesis. And goes on to talk about how he did that. And then in 1960s, he proved that plants exposed to light flashes after their temperature was raised produce delayed light emissions for a limited time. For his work, he received the Kittering Award from the American Society of Plant Physiologists. In tribute to Arnold, Jean Labarelle, that's a French name, and I know I'm messing it up, French scientist who visited him in March 1957, called him a giant and pioneer of biophysics and photosynthesis. He described Arnold as straight, plain, even-tempered, attentive, and nice, and also as a utterly methodical, but resourceful, and imaginative. Now then, he goes into the 1939 story that you've already heard. He worked for a year at Niels Bohr's Institute, and at the institute he met Otto Frisch, the nephew of Leisner. Christmas holiday in 1938, it goes into the same story you just heard. And so he was the one, because of an understanding of biology, that came up with the term fission.
I had no idea. Thank you. Good remark, Ray. Ray and Bill, thanks for bringing that up. And I like his innovation. I saw that. Blackboard in the living room. What a great idea. I think I need that.
Let me read this just a bit more. You work in a microbiology lab, Frisch said to Arnold. What do you call the process in which one bacterium divides into two cells? Binary fission, Arnold replied. I don't want a two-word name, Frisch said. Can I call it fission alone? Arnold said, yes, sir. That's it's a good thing you didn't use the whole name.
Well, and sometimes that is appropriate because it doesn't happen often, but sometimes there is tertiary fission of nuclei, where uranium, when it splits, goes into three pieces. That's rare, but it is known and measured. But no, he did not need to use that term, two terms, right?
In 1966, he got the Atomic Energy Division's Enrico Fermi Award. He and
Wow. Interesting. I had no idea there was an Oak Ridge connection there. Amazing. Back to Fermi. So in 1938, of course, Hitler took Austria. In 1938, he made a deal with Mussolini about the same time. Mussolini originally, from 35 on, had promised he would not persecute the Jews, but he changed his mind in July of 38. He issued his first anti-Semitic proclamation in September. Fermi's wife, Laura, was Jewish. Passports in Italy were stamped as Jewish, if you were such. For some reason, hers didn't get stamped. They knew that with this new law, they knew that they had to leave Italy. Fermi was famous. He had invitations to come and lecture in the US. And there was this possibility of a Nobel Prize. He'd been warned, and this was probably part of the thinking, a way to get Fermi and family out of Italy was becoming more hostile to Jews, was to have him go to Stockholm to accept the Nobel Prize. He deserved a Nobel Prize, but this was part of the strategy. The board was arranging. He was on the Nobel Prize committee. And so indeed, on November 10th, the call from Stockholm came, where the Nobel Prize was awarded to Enrico Fermi. 1938 this was. And the same day, the new racial laws were announced, where Jewish teachers were dismissed and Jewish children were excluded from private schools. Jewish lawyers and physicians could only do business with other Jews, not with Aryans, as they were called. Also, passports were withdrawn for all Jews in Italy. So as Germany, up until at least 38, they were driving Jews out of Germany. The intelligentsia, Mussolini withdrew all passports. They planned to go to, Fermi planned to go to Colombia for 6 months in 1939. But the Nobel Prize that was announced gave him a reason to leave Italy, go to Stockholm. He was able to take his family. They couldn't take all their possessions because that would be too suspicious. It was surprising somehow that Laura Fermi's passport was not stamped Jewish or taken away from her. Should have been. No one really understands whether that was a mistake or whether Enrico Fermi arranged that or whatever. Anyway, they were able to get out of Italy and went to Stockholm to accept the Nobel Prize, and then came to New York January 2nd, 1939. That's just about a week before Bohr arrived. By the way, there's a very good book. Bohr became a political activist, died in 1954. Enrico died in 54. She lived until 77, and she wrote a book called Atoms in the Family that I have on my bookshelf down there. A good story about the Fermi family. Luckily, Bohr heard about this discovery, making barium from uranium fission. Before he got on the ship, in the 8 days across the Atlantic, he and his colleague, Leon Rosenfeld, worked out the first rudimentary theory of nuclear fission. They arrived on January 16th. The Fermis were there. They had arrived a week or two before, so they were there in New York to meet Bohr. He and Roosevelt arrived on the ship. John Wheeler was there. He was a young professor of physics at Princeton. His job was to meet Bohr and bring him out to Princeton, New Jersey, for his stay at Einstein's Institute for Advanced Study. Wheeler only lived to be 97. He only died in 2008. I met him once or twice at conferences. Great physicist. So as soon as they arrived, Bohr went with the Fermis to do some other things, but Wheeler took Roosevelt immediately out to Princeton with this news of this discovery from Berlin, Stockholm, Copenhagen, and Roosevelt right away gave a Monday evening talk at the Institute of Advanced Study about this new discovery. Another one, Eugene Bicker was one of the Hungarian Jews who got his degree in Germany and then left. He was now also at Princeton. Szilard, Leo Szilard was there. He was visiting. He was working in England, but he came to visit for some reason in the US. So he was there also, two old Hungarian friends. Szilard, I sort of told that story. He was one of these 7 or 8 Hungarian Jews that flew from middle class to Budapest, Germany, then got their physics training and had to go abroad. He had the vision for anybody of perhaps you could use the energy of the nucleus to split it somehow, to make even a bomb, make a chain reaction. In part, he knew H.G. Wells, the guy that wrote War of the Worlds when he was doing it. And Wells wrote this book about the Great World War in 1956, because some of Germany versus the world, basically. And a great weapon had to do with the atom, within that war. So H.G. Wells had this vision, and Szilard knew something about physics, and so he was always looking for that element that you could split to release energy to make a bomb. He thought maybe it was beryllium at first. That didn't work. He thought it was iodine. That didn't work. So he filed a patent in England in 1934, trying to patent this idea that you could have a chain reaction. He was looking for an element where it would absorb 1 neutron and emit energy and 2 neutrons, so that you could have a chain reaction, emitted neutrons causing other things to emit neutrons. And he tried to patent that, but then withdrew the patent when he could not figure out which element could do that. Well, Szilard was stunned by this announcement. All of a sudden, he saw the future he'd been dreaming about for 5 or 10 years. And Szilard figured out that if uranium not only fissions, splits into 2, but if it also emits neutrons, then you're at the doorstep of a chain reaction and a weapon. Fermi was down in Columbia, came after Stockholm, got his Nobel Prize, came to New York, got a temporary position at Columbia University, and he heard this news this day, January the 16th or 17th of 39. He realized that his Nobel Prize was partially a mistake. And he was partially got it because he had made the first element beyond uranium by neutrons being absorbed by uranium. In fact, he had made nuclear fission and did not realize it. There was a,
But Lee, both things happen. You can get transuranics
yes,
by neutron radiation also.
that's right. So he was actually also making plutonium, but had no way to know that. You're right. So this then produced a rush of activity. George Gamow was a Russian-born physicist who came to Germany and then came to George Washington University. He was hired to be on the faculty. He was there for about 5 years before this all happened. He brought on to the faculty engineer position Edward Teller. He had another one of these Hungarian Jews who came through Germany and had to leave Germany. And they got in a tradition of having annual physics meetings like Bohr had in Copenhagen, bringing together the great physicists and chemists of the world to talk about what's happening now. It turns out that soon after Bohr arrived, this is one reason he came at this time, January 39, was to attend the fifth of these conferences of theoretical physics at George Washington DC, organized by Gamow and Teller. Well, the word of fission spread rapidly, and various people were trying to then verify, could this be right? Turns out that in Chevy Chase, Maryland, there was a small, newly built Van de Graaff accelerator. And these people were there. And this guy, Merle Tuba, obviously a Norwegian name, had built a Van de Graaff accelerator, a linear accelerator, a small one, but now they're common. Built the first one there at this laboratory in Chevy Chase, Maryland. And when they heard about this accelerator, they realized, geez, they could use an accelerator, do a quick experiment to verify this accelerator could generate neutrons in a certain reaction. Use those neutrons to hit uranium to verify what Otto Hahn proposed and Lisa Meitner proposed. And so because they were all here for this conference, late January 39, they went on this experiment. Fermi was there, and Bohr was there. And that's one of Bohr's sons, Eric Bohr. I never met him. Maybe he was dead by the time I arrived as a young postdoc at the Niels Bohr Institute in '68. Niels died in '63. His son Ola, by that time, was the head of the institute. I think maybe Eric had died by that time. I forget the details. Never met him. Anyway, these were very important people that were there for this conference, and they fired up that early Van de Graaff accelerator. And there's Fermi and Bohr and Rosenfeld looking at the instruments and verifying, my goodness, at this Department of Terrestrial Magnetism, that there was indeed nuclear fission happening. Fermi also was at Columbia. He did a verifying experiment. Irene Curie and Frederick Joliot quickly did a verified experiment in Paris, realized they messed up. They had it in their finger. They published a paper in September 38. They had the data. They just didn't go the right step, didn't do the right conclusion. So they could have had the Nobel Prize. They missed it. Zohar had solved now the vision of a chain reaction in a bomb. Newspapers picked up the story since this conference was in DC, is where the news was announced. So this became public fodder. People in Berkeley we haven't talked much about Ernst Lawrence. He is the guy that invented the calutrons later, but he invented the cyclotron in Berkeley, got a Nobel Prize for that, a circular accelerator. And there was one of Lawrence's colleagues was getting a haircut in Berkeley, picked up the newspaper that was to get his haircut and saw this headline or this story on the front page about this discovery. He jumped out of his chair before the haircut was finished, rushed up to the hill, the Berkeley lab, told Lawrence they fired up their cyclotron and verified the experiment and also kicked themselves. They'd been doing similar things. They missed it too. Oppenheimer was in Berkeley. Oppenheimer and Lawrence were good friends, both young physicists on Berkeley physics faculty. Oppenheimer was a theorist, and when he heard about the news, talked to Lawrence about the very fine experiment done in Berkeley, he immediately saw the potential for a bomb, which is ironic since he then later became the head of the Manhattan Project. Otto Hahn won the Nobel Prize in chemistry in 1944. Fritz Strassmann did not share in the Nobel Prize. Not sure why. He was the junior woodchuck in the collaboration, I guess. Hired chemist. And Lisa Meitner did not share in the Nobel Prize, even though it was she that figured out the physics of it, what was happening. There were efforts to get her the Nobel Prize later. Also, some efforts to get Otto Frisch the Nobel Prize later. That didn't work. And so it's always been a bit of an unfortunate thing that Lisa Meitner never got or shared in a Nobel Prize in physics. Now, one of you is doing Lisa Meitner. You are. So there's good stories to tell there. So, so now the world was all different, where verifying experiments were done. People realized that uranium was splitting in roughly two pieces when it got hit with a slow neutron. It was not verified that the neutrons were also emitted. That was the next step. Szilard really solved that possibility. Now we know that when a neutron hits uranium-235, it splits into two roughly equal pieces, gives off energy, gives off 2 or 3 neutrons per fission, and those neutrons, if they are moving slowly enough, could be captured by another uranium nucleus, which then fissions, gives off more neutrons, and so you get a chain reaction. We have neutrons being emitted step by step to make a chain reaction go. That's the vision that Szilard saw. By this time in early 39, no one verified that neutrons were being emitted, that you could multiply neutrons in this fission process. But that's what Fermi and Szilard went to work on at Columbia, to show that neutrons were also emitted. And of course, then things accelerated even more, where the German physicists, those working in the US, were all trying to verify or detect if neutrons were multiplied. If that were the case, then you could consider making a bomb. Another step along the way is, if they are emitted, how fast does that process go? If it happens slowly, then you'll never have a chain reaction. You'll never be able to build a bomb. Later on, a year or so later, then people in England did the calculation and said, oh my goodness, that process is fast. And then people knew you probably can use this to make an atomic bomb. Ray, did you have another story you wanted to tell?
Yes, I do. We can,
Come on up. I'll stop here.
okay. We can talk about Oak Ridge and in a number of ways. We talk about material that,
Right back.
that we use there. First material that they were concerned about and needed, of course, was large supply of uranium. And then later, at about the same time, they were trying to build the calutrons. They needed a large supply of silver because of the And then even later, in the early 50s, they needed a large supply of mercury. So in the mercury, case of the mercury, all of the reserve in the nation was actually brought to Oak Ridge. And that was never told, no one knew it, but it was all here. In the silver, it was 14,700 tons were brought and used as electrical conductors. Now, the story about the uranium is a little different twist. During the late 1930s, where he's been talking about here, this person in the Belgian Congo, his name is Singer, S-E-N-G-I-E-R. He saw Germany buying up his uranium ore out of the uranium mine in the Belgian Congo. And for 2 years, he stopped selling his ore to Germany. And he packaged that ore up, brought it over to New York City, and put it in a warehouse on Staten Island. Did that for 2 years.
What was his name?
Singer, S-E-N-G-I-E-R. And when the Manhattan Project started, Colonel Nichols and Groves were talking, of course, and they realized we need a large supply of uranium. And the mine in the Belgian Congo was known to be a large source of lots of material. In fact, the mine is still active even today. I don't know that uranium may be coming out of it, but other materials have. So Nichols went to Mr. Singer and said, look, you've got a uranium mine. We need some uranium ore. He says, I knew you were going to need it. I've already brought it to you. It's in a warehouse on Staten Island. Now, that's interesting. One person decided that Germany would not get his ore, but the United States would. And he worked for 2 years, shipping all of it he could over to the United States so that would be available. So he had some knowledge about what was going on. In the late 1930s, you notice newspapers were talking about this uranium. It was well known throughout scientific circles, and even general public began to pick up on this idea of uranium. So he realized he had something that would have a huge potential in the future. So Nichols took that ore. Now, one of the interesting things about that ore, unlike today, and they're still mining uranium today in Colorado, up in Canada, but in that ore, about the largest percentage of uranium you'll find today is less than 1%. It's a very small amount of uranium in the ore. In the ore that came out of the Belgian Congo, some of it was as high as 60% uranium. Now, that was very important at that time to get that much uranium out of that ore. Now, it was processed, and when it came to Oak Ridge, it was ready to be used. It was made into uranium chloride mixture, and that was what was put into the Gadgetron. When it went over to the K-25 gaseous diffusion, it was put into a uranium hexafluoride mixed with fluoride, and that was what was used in the gaseous diffusion. Now, doesn't that make you wonder what happened in that area in the Belgian Congo in the far distant past to leave a very rich supply of a high percentage of uranium in the ore that's coming out of that mine? But that's one of the stories that we'll share with you about how single individuals may have made decisions that changed the course of history because of who they decided would get the uranium. Or later on, we'll talk about Copenhagen and what maybe a decision might have been made there. But any questions about the uranium ore? Or I can talk more about silver or mercury. Those are the large quantity materials that have come to Oak Ridge over the years.
It took a while once again, when did the U.S. government realize that uranium ore was sitting on Staten Island?
Yeah, it was that conversation between Nichols and Singer,
In
and that was in 42.
42.
Yeah.
Okay.
In fact, it was before, if I remember right, it was before they actually, well, it had to be after September because Grove wasn't in charge until September the 17th. And they started building Oak Ridge in November the 22nd. In 1942, they started building the administration building. Now, they didn't get the process buildings going up until actually middle of 43. So it was somewhere between late 42 or early 43 when that conversation had taken place.
Where else would Groves have located the main Manhattan Project lab east of the Mississippi, if not Oak Ridge?
Now, there is a story that there were at least 3 places being considered. A couple of them in Tennessee, but one other one in Tennessee is I can't remember the name of it, but if you look on the map, it's a very large garden up in East Tennessee, and it's enclosed by ridges. It has a very flat valley in between those ridges. And Lamar Alexander is the one told me that was being considered. So I had to go do some digging and research for him because he loves to tell those stories. And in fact, it was. But all during
toward,
1942,
Johnson City or something up
yeah,
that
it
far
was
east?
up in that area. Yeah. And in the summer of 1942, the Tennessee Valley Authority and the Colonel Marshall, who was in charge before Groves, he and the Tennessee Valley Authority were actually looking at areas in Tennessee, but he was dragging his feet. He didn't want to make the decision about where, I'm not sure why, but immediately when he was no longer in charge and General Groves was put in charge, he actually cut the first meeting short so he could catch a train to come down to Tennessee and check out this area. And on that trip, he actually made the decision to go ahead and buy the property, some 60,000 acres. So Groves moved quickly.
And then are these stories where some farming families were forced to move when Norris Dam was closed?
Yeah.
They moved to what is now called Oak Ridge. And then they had to move again.
10 years later, yeah. So they had to move out in 32, 33 is when the dam started. And they moved down to what was in New Hope and Robertsville, Loyston, those little communities there. And then 10 years later, they had to move. Some people had been kicked out of the Smoky Mountains, Cave Cove, some 20 years early. Went to Norris and then came to what's now Oak Ridge. Had to move 3 times in 30 years. Every 10 years, the government come along.
That's bad luck.
Yeah.
I thought the train was a factor in the bridge area because they were moving all that grain from New York by train.
It did have a railroad. That's one of the positives for it, because the railroad did run through there. The river was also a good positive aspect. The other was the proximity to Norris Dam for electricity. They thought that would be a source of electricity. And TVA told them, if you'll build it within 5 miles of the power line that's running toward the southwest, we'll be able to provide electricity. Now, TVA had to build 6 more dams to get enough electricity to run Oak Ridge. But that did come into consideration. But you probably didn't hear this, so I'll tell it quickly, though, for your benefit. The rest of them have heard this story. What really made the decision to select Oak Ridge is probably Senator McKellar, when he was asked by President Roosevelt if he could hide some money from the Manhattan Project, that he didn't want the press or anyone else to know what it was being used for. Senator McKellar said, yes, Mr. President, I can do that for you. Just where in Tennessee you want to put that? That likely had more to do than any ridges and valleys and rivers and proximity. to-
And McKellar was chair of Senate Appropriations.
Yeah, appropriations.
Yeah, Phil.
Oh, we watched one of the movies that you were recommending called, I think it's called Day One or something. It's a real movie made in 1989. It really does go into the whole project. And when Rhodes, Leslie Rhodes was appointed, he was really a Vince Lombardi driver. And he clashed with Savard really seriously. But I was really surprised to learn he liked Oppenheimer. He really liked Oppenheimer. And Oppenheimer really fit into that mode of operation. Really being an academic, I was kind of surprised to hear that. Because a lot of class with him because he was an academic in New York. He wanted to have meetings, share everything. Rose said, you don't share anything.
Yeah, it's amazing the Manhattan Project worked.
Yeah.
There's all the diverse set of personalities. Of course, it was terror. It was terror that the Germans would get there first.
That's it.
And then Germany would have won the war.